sa Nicole Becerra, and today we'll discuss solving linear programming, maximization, and minimization problem.
I am Leslie Abapo. Today I'm going to explain a linear programming, a problem that involves maximizing profit in a factory setting. We will look at how to determine the
Start with the problem statement. We have a factory that produces two products, product A and product B. Each unit of product A requires 2 hours of labor and generates a profit of 30 units. On the other hand, each unit of product B requires 3 hours of labor and generates a profit of 50 units. The factory has a total of 120 hours available for production. To solve this problem, we need to define our variables. Let X represent the number of product A produced. Let Y represent the number of product B produced. Our goal is to maximize profit, which we can express with an objective function. The total profit P can be calculated as profit equals 30x plus 50y. This means for each unit of product A produced, we earn 30 units, and for each unit of product B produced, we earn 50 units. Next, we need to consider the constraints. The main constraint here is labor hours. Since each unit of product A requires 2 hours and each unit of product B requires 3 hours, we can express these constraints as 2x plus 3y less than or equal 120. This means that the total hours spent on both products cannot exceed the variable 120 hours. We also have non-negativity constraints. X or greater than or equal 0, we can produce a negative number of product A. Y greater than or equal to 0, similarity for product B. Now, let's visualize this. To graph our constraints, we find the intercepts of our labor constraint. If we set Y equals 0, we find X equals 60, which give us the point 60 and 0. If we set X equals 0, we find Y equals 40, giving us the point 0 over 40. This allows us to plot our constraint line on a graph and identify our feasible region where all constraints are satisfied. Next, we need to find the vertices of this feasible region. The corners will help us evaluate our projective function we have. The points 0, 40, and 60, 0 from our intercepts. We also find another intersection point by solving the equations simultaneously, which give us 30, 30. Now, it's time to evaluate our objective function at each vertex. 1 at 0 and 40, profit equals 30 multiplied 0 plus 50 multiplied 40 equals 2000. 2 at 60 and 0, P equals 30 multiplied by 60 plus 50 multiplied by 0 equals 1800. At 3 at 30, 30, profit equals 30 multiplied by 30 plus 50 multiplied by 30 equals 2400. Conclusion, the maximized profit, the factory should produce 30 units of product A and 30 units of product B, achieving a maximum profit of 2,400 units.
Today, we will tackle about solving linear programming minimization problem.
So for today, we will be solving linear programming minimization problem using Polya's 4-step process. So for our example problem, A company produces two types of products, X and Y. The production process requires labor hours and has associated cost, and the company needs to minimize its production cost while satisfying resource limitation. The company has a total budget of $72 for production cost and 18 hours of labor available. The objective is to minimize production cost while respecting the given budget and labor constraints. So I will be using Polya's 4-step process for problem solving. Polya's method involves 4 steps: understand the problem, devise a plan, carry out the problem, look back, and check the result. Let's walk through these steps to solve this linear programming minimization problem. Step 1. Understand the problem. First, let's understand the problem and the information we are given. Product X. Each unit costs $3 and requires 2 hours of labor. Product Y. Each unit costs $4 and requires 3 hours of labor. And for the budget, the total budget for production is $72. While for the labor, the company has 18 hours of labor available. The goal is to minimize the product cost of these products while ensuring that the production cost does not exceed $72 and the total labor does not exceed 18 hours. And for our next step, we need to devise a plan. Next, we devise a plan to solve the problem. Define decision variables. Let's define our decision variables. This represents the number of each product produced. But for our problem, let X1 is the number of units of product X produced, while for the let X2, number of units of products Y produced. The objective function will be minimized. Z equals 3x1 plus 4z 4x2. Next is we write the constraint. The company has 2 main constraints. The budget constraint, the total production should not exceed $72. So 3x1 plus 4x2 is less than 72. And then we have the labor constraint. The total labor hours should not exceed 18 hours. Since product X requires 2 hours per unit and product Y requires 3 hours per unit. We have there 2x1 plus 3x2 is less than 18. And for the non-negativity constraint, we cannot produce negative quantities of product. So x1 is greater than 0, then x2 is greater than 0. Next is the graph constraint. So graph the constraint, we solve each inequality for x2 in terms of x1. From the budget constraint, 3x1 plus 4x2 is less than 72. Solve for x2. We can see there x2 is equals to 72 minus 3x1 over 4. From the labor constraint, 2x1 plus 3x2 is less than 18. Solve for x2. x2 is 18 minus 2x1 equals 3. Plot both equation and the coordination plane to form a feasible region. The feasible region is where both constraints overlap, and it is bounded by the axis and the constraint lines. And then find the corner points. Next, we identify the corner points of the feasible region which the points are constraint lines intersect or where they meet the axis. And for our intersection of the budget constraint and labor constraint, we have to solve this as you can see on the paper. After solving using substitution or elimination, we find the intersection point is x1, x2 equals 12 and 0. Intersection with the axis for the budget constraint, when x1 equals 0, x2 equals 72 over 4 is equals to 18. So the point is 0 and 18. For the labor constraint, when x2 equals 0, x1 equals 18 over 2 equals 9. So the point is 9 and 0. Therefore, the corner points are 0, 18, 9 and 0, and 12 and 0. Next is we evaluate the objective function z equals 3x1 plus 4z2 at each corner point. At 0 and 18, we solve for z is equals to 3 open parenthesis and close parenthesis plus 4 open parenthesis 18 close parenthesis is equals to 72. And at 9 and 0, same process, and for 12 and 0, same process too. Finally, let's look back and check the result. From our evaluation, the minimum cost occurs at the point 9 and 0, where the total production cost is $27. This is the optional solution of the problem. It means the company should not produce 9 units of product X and 0 units of product Y in order to minimize production cost.